Hello everyone, and welcome to yet another session of our literature survey season update. In fact, this is the second literature survey session of the day. If you missed it, we had a session on ML for neuroscience just a couple of hours ago. This session will be on ML for healthcare and it will be presented by our very own Harriet Huang, who works as a data scientist at Suhas Pai, where she is working on some fascinating problems in the field of healthcare. So over to you, Harriet.
Thank you, Suhas, for the introduction. Hi everyone. I'm very honored to be able to share with you that I have come up with recently for healthcare. Today's survey will be mostly talking about the applications and challenges in applying machine learning for healthcare. So there will be two papers we will be going through today. The first one is by Dr. Zhang and Wang. The second one is by three authors. So let's see what they are. We will talk about what are the problems in healthcare machine learning mostly will be solving. So the first one, it will be investigating how do we integrate heterogeneous data types for precision medicine. So in this case, we will see how is the machine learning combining, say, images as well as text together into one model to better predict medicine. And then the second one, we will also take a look how the security and privacy is being preserved for healthcare data. And then there are also other applications in machine learning for healthcare. They are you can automate the clinical process. For example, you can predict medical code based on clinical notes. And then also there are also medical and policy intervention that you can do based on the insights that machine learning find. And then of course, there are the very popular application right now in drug discovery. So using a graph convolutional neural network to invent drugs. And then there are quite a few companies, even in Toronto, our local communities are doing the cool work for that. And then we will also briefing about two most popular methods involved in this fascinating field. They are applying graphical convolutional neural network as well as the most latest advances in natural language processing. And of course, we will also investigate how one of the research paper is combining these two methods into one model. And then the data sources that we will talk about are images as well as electronic health records. So neural images are things like brain connectivity graphs, and electronic health records actually are already a big open source project right now, which is maintained in the Mimic 3 dataset. That's a very widely used dataset, so you can investigate that in GitHub. There's a recent publication by University of Toronto. They have come up with a entire pipeline to do ETL for that giant data set. So this is the preview of the first paper we will investigate. So it is talking about how do we do integrative analysis of the patient health records, which is text, and neural images, which is a graph, together in a memory-based graph convolutional neural network. And the second paper, we will see how is preserving security and privacy in big healthcare data are doing right now. So this will be a survey on the most latest advances. And so for the first paper, we will firstly take note of several key concepts. The first one is it is combining two different types of data sources, namely text and graph. Because in most earlier research work, it will be either text or graph, so only one type of data source to do the precision medicine. But this one, it will investigate combining the two. And then the second one, we will also know the concept of ROI in graph. So it's region of interest in a brain connectivity graph. It will embed this ROI into a ROI vector and then integrate it with the vectors embedding from text. So there are already real life applications and opportunities in applying this research. So, for example, University of North Carolina Healthcare, which is a not-for-profit community healthcare center, has already been using this for the huge quantities of unstructured content to predict readmission risk for timely intervention. So therefore now it can providing a safer care for high risk patients. Maybe it's not specifically using this paper's research because this paper's research comes pretty recent, but this similar type of application has been in place in many places. So this is graph for ROI in brain connectivity images. For example, on the left-hand side, this is a graph for a brain, and then when you zoom in, so that this red rectangle zooming one part of the brain, and then when you extracted that zooming that part on the right hand side, so you can see it's like a cubic. So on each of the voxel, it's the number, is the parameter estimate for that voxel. So that represents the amount of brain connectivity in that voxel. So this is the ROI, so the region of interest analysis. And then, so in the first paper, it used graph convolutional neural network to make each of the ROI node as a node and also model the relationship between each of the ROI node. The very special part of this application is that usually in graph convolutional neural network, it's 2D, but because right now we are modeling a brain's connectivity graph, so it will be using a spatial graph construction to model the spatial positions of the ROI node in the position of the brain. So therefore, it will use the region coordinates, so to model the spatial relation. So therefore, each of the ROI node will be a 3D coordinates. So this research work is motivated by the work of this paper, distance metric learning using graph convolutional neural networks, application to functional brain networks. So specifically applying GCN to brain image. And this is how the architecture of the whole model works. So you can see that the brain images and then goes into the GCNs, and then on the upper front it will be the text, the clinical, so it will be a longitudinal data coming in, and then in later in the different health hubs, it will combine together to make the final outcome. If this graph is a little bit too complicated at first sight, don't worry. So we will dumb it down and then simplify it in this next graph. It looks much better, right? Like more simplified at least. So this is the whole memory GCN network. So it include two parts. The first part is the GCN part, which process the brain connectivity images, and then the second part is the memory networks that process the longitudinal text records. But a special point is that it actually uses two memory networks to process the text sequences. So we will actually take a look how the two work together and then ultimately combine with the graph of the GCM. So the key points to take note here is that so the two memory representation here represents one is input memory vectors, one is output memory vectors. So when I'm actually reading this part, what I take analogy from is um, the self-attention network in Transformer. So if you can recall, for each of the node, the tokens that it actually produces three copies of each of the word tokens. So key and value and query. So this research work here actually I think draws analogies from that. Instead of making three copies of each of the word token, it makes two copies. So one copy is the input memory vectors and another copy is the output memory vectors. So input memory vectors are used to calculate attention weights given the ROI vectors from the graph. So after calculating this attention weights, then it applies this weight to the output vector, memory vector from the same token, and then combine it to become a context vector. So if you read from here, then probably this also becomes very straightforward and similar for you from the self-attention network. And by using input memory vectors to be combined with a graph, I think this also draws analogy from the sequence to sequence neural network. So for sequence to sequence, is that when you are trying to output a sequence, then it actually takes that input in as a parameter to the input vectors to come out with the attention. So your attention weights actually depends on which step you are in your decoding step. So same thing here. The attention weights of the input memory vectors depends on which part of the ROI vectors that you are focusing on your brain connectivity voxel, and then that comes into as a parameter when you are calculating the attention weights for your text vectors. So and then after these two memory networks, then it will combine with the ROI vectors from the GCN graph. So we can take a look. So this is one hop representation. So you can see here when on the left hand side, when the sequence of the longitudinal text records comes in, then it produces two copies. So one is embedding A to produce input memory vectors, and another one is embedding B, which is to produce output memory vectors. And then just to take note that these dimensions, so this embedding A is actually a matrix multiplication step, and then the dimension of these two vectors, they should be the same. And then this input memory vectors will then take the parameters from the brain connectivity matrix, the network through the GCN, which produces the ROI vectors, and then to calculate the inner products for the attention weights. So you can see this weights now alpha is calculating, and then it will be combined with the output vectors to produce the context vectors. So now this whole left giant part is processing the text data, and then integrating with the brain connectivity graph, and then later on, then it will combine with the ROI vectors together. So now the two data sources merge to produce the final output right here. So now this becomes much better, right, than your first site. So this is the experiments in this precision medicine taking two heterogeneous data sources. So you can see that this fusion, so the memory GCM bilinear is on the last row. It's actually improved a lot of the previous result. For example, even with just the most basic attention GCN, it has increased a little bit from there. And so then we will take a look at how the security and privacy preserving is doing its work for healthcare. So firstly, why do we need to take no importance of that? Just to, like, even for the latest news, the North Korea leader Kim Jong-un, as Trump call him the little rocket man. He doesn't want you to know his health, right? And then actually, from what I heard, he practices BYOT. So what does that mean? Bring your own toilet. So from what I heard, even when he went to visit Singapore to meet with Trump, he actually brought his own toilet just because he doesn't want anybody to know his health conditions. And then there are several risks for this type of healthcare data. So, for example, there will be breaches as shown in the as shown in the RESPIN 7th annual breach report. In 2016, a single year, the hacking attacks on healthcare providers actually were increased 320% in that one single year, because not only data is gold, but health data is even more valuable than gold. I don't know what that is. And then the aspects of tackling this field comes with, firstly, you need authorization in data collection. So that's the privacy part, and also how you are sharing the data, and as well as how you're using the data. So the data collection, sharing, utilization, any of these steps actually needs cautious. So the method that is being used in this field includes, per se, there's de-identification, there's data masking. So in these two methods, for sure, you will see that the name entity recognition algorithm really comes in to help. So you can identify, so you can mask people's name, mask people's age, map people's birth date, or if you don't want to be too so complicated, then you will just for simple things, at least you should replace them by broader categories. So for example, not individual values, but let's say if it's a address, then it will become a zip code. Or if it's a birthday, then you replace it just by the year or something like that. So there's a different.
Harriet,
Yeah.
if I can interrupt you for a second, there are questions online. The first question is, what's the difference between embedding A and B?
Yeah, right. So if we go back to embedding A and B, so embedding A is to produce, if you remember the self-attention network in Transformer, so you produce 3 copies of the of the word vectors, so key value and pairs. So I think this is exactly the same as that. So it will just to generate different copies of input memory and output memory for different uses.
Okay. Let me see if there's. It seems like we have to move on to the next question. The second question is, I was going to, they're saying, why are they called input and output? What is the difference?
Right. So the input means that it is to be inputted to be combined with the ROI vectors from the brain graph to calculate the attention weights. But then, so in this case, if you draw analogy with the self-attention mechanism in transformer, then it will be the the key vector. So it is to its function is to calculate the attention weights, but the output memory vector is like the value vector in self-attention mechanism in transformer. So it uses the attention weights calculated from the input vectors, and then that weights then will apply to the output vectors, and then that output vectors is actually the final vector to be aggregated with the attention weights, and then eventually goes into combining, merging with the graph output from the GCN. So I guess that is the difference.
Okay, and the next question, they're asking if you can describe what EHR is. Is it structured data? Is it a basic patient information?
Right. So electronic health records is short for EHR, right here. Um, so so it's unstructured. So it actually combines with different types of information. So for example, there are lab tests. There are clinical notes, like for say doctor's notes. There's also demographic information. So basically, it's that giant patient health records. So an example is the MIMIC 3 data. I believe it's either MIT is maintaining it, or I think pretty much, yeah. So it's a giant one, denominized, and then it's longitudinal. So it's like a transactional data, but pertain to one patient. So all aspects of that patient's health records.
Okay, thank you. That's all the questions we had online.
Perfect. Thank you. Okay, so thanks for the question. So we now will go back to the privacy and preserving. So yeah, we were here talking about the difference between security and privacy. From what to distinguish the difference is more that so privacy is more that how you are able to access the information. So security is more like how are you handling it. So for say, are you encrypting it, are you firewalling it, and so on. But there's a fine line distinction between the concept of the two. So this is the data handling cycle for any type of healthcare data. So firstly, in every single one step of this cycle, you actually need security and privacy preserving strategies. So from just the simple data collection, so you need to be able to have authentication steps, access control, and so on. And then data transformation. So you will be filtering, classifying the data, and so on. So you can also take a look at here the legend. When the color is deeper, then it means that there's more risk involved. So the highest risk involved actually surprisingly is in the data modeling part. I guess because that's what most people are afraid of. So what you are using their health data to do what, right? And then what, for example, that's why these AI ethics research now are all coming out. So people are actually researching different methods to, like you cannot just modify human genes and all that. So that's a huge controversy in all that aspects. So that's why I guess it reminds us that we cannot just focus on the techniques, the scientific part of it, but the humanity part of it is even more important, because when your scientific methods evolve so much, but then if you don't have good ethics control and governance, then it might just blow up the earth. And then the next one is it will talk about each of the specific methods that are handling in security and privacy preserving. So for say we just briefly talked about is name entity recognition in data masking, and also this method of anonymity in de-identification. So data anonymization. And when the K is higher, then it means that it has a lower probability to be re-identified, because sometimes when your data after de-identify, if you linked it with some public data, then the K will measure what is the probability that actually this data will be re-identified, right, from hacking and so on. So there's also other cryptography methods in the de-identification process as well. So this table gives you a list of the most recent approaches used in big data privacy. So it mentioned about differential privacy methods in handling that, and also it also talks about say the data mining techniques in Hadoop, the big data system, to solve without utility degradation, and so on. So you can take a list of this table, and then it also mentions about their limitation. So for example, when you are doing the data mining techniques in Hadoop, the execution time might be affected by the noise sizes and so on. So there are also other interesting research in machine learning for healthcare. So, for example, in there are already quite a few people applying different methods in the COVID-19 cases. For example, this paper quantifying effects of quarantine control methods in COVID-19. So it actually uses the physics motivated neural network to measure the effect, because traditional conventional neural network actually wouldn't be completely work for that quantification. And then so this is their results from the method. As you can see, so this is a case for Italy. When the quarantine strength increases, the dotted line is the predicted confirmed cases, and then the red line is the actual is the prediction, and then reverse. So the dotted one is the actual infected, but then the red line is the prediction. So it's not very obvious, but like somewhat the slope is actually kind of like slowing. But then the South Korea case is very obvious. I guess it's because, because this quarantine strength you see in Italy, it doesn't increase as sharp. So therefore, the strength in the confirmed cases, the slowing curve is actually not so obvious. But if you see this South Korea model, it the strength of the quarantine really exponential growth. So therefore, there are both the prediction as well as the actual infected cases actually has a more obvious sign to slow down, which I guess is affected on the table that we see every day as well. And also, this is the USA case. I guess it's very depressing that you don't see any like slowing here on the left hand side.
Harriet,
Mm,
if I can interrupt you for a second, there's a
yeah.
question online. They're asking, what's the measure of quarantine strength?
Um, that's a good question. Okay, so I actually didn't really dive into that. How do they define the quarantine strength? I guess it's the different policies, like for say, like the closure of the business, and then the social distancing, and then so that and all that. But you're welcome to dive into that paper to read through like what are the complete list of definition for quarantine strength. Yeah. Okay, so now we move away from the depressing thing. So there are also, per se, applications in drug discovery. So actually, there's also like companies I think already actively doing that. For say, even in Toronto, I think it's called Bench Science, right? They're doing drug discovery work. So this paper actually will use GCN to do drug discovery. So each of them, so just to model the molecule and their interactions in for drug discoveries. And so this is also a very active research going on right now in healthcare. And then we can also, draw some importance about the challenges in all of these models and key factors. So for say, one big thing is that even in all those prediction model that we've seen using regardless which fancy method, but they have to answer the question of causality, because um, only causality model can answer the question what if, and then to be able to really do prescriptive measures. So for say you intervention models, so by so you predict something now, so what, so you want to be able to, because a good chunk is that how you actually use that thing to improve people's lives, and then to be able to intervention model, so then you need to answer the question what if. So what if I do this, then what will change? Like the classical ML models cannot answer this question. Only causal model can. So here comes into difference between a causal model and predictive model. So predictive model, which is the most classical ML models, does not answer that. Even though it can predict, but it cannot draw causal inference. So that's one big chunk of that. So that's why I think the causality model now becomes focus of many people. From what I saw the news, Yosha Banjo now focus a lot on maybe trying to um, come up with better causal models. And then another point is in healthcare data, just like any real life data, there are a lot of missingness. So either from measurements or from or from any reason. So it's missing. And so then how to deal with all those missing data then is another big problem in the real applications. So there are different types of missing data sources. So the easiest one is those data are missing completely at random. And then the second easiest is missing random given some variable. So it's not completely random, but given some variables, then it's missing random. So then it will be different strategies to deal with just this different two type of missingness. So if it's missing completely at random, so then life is much easier. So the remedies will just be you just drop the incomplete observation, just drop the row. If like in the relational data table, you just drop that case. But then if it's not missing completely at random, then you cannot just drop the observation. Then you have to use different imputation methods. So imputation means that you have to fill in the blank of the missingness. So I believe this in statistical research, there are like a whole field just doing research on how to do imputation. And then I believe in many of the statistical packages, there are also imputation methods as well. So you're very welcome to do research on that as well. So that comes into my presentation for today.
Thank you so much, Harriet. Excellent presentation. Now we're going to open the floor for questions. We already have a question regarding the COVID paper. They're asking if there was an assumption regarding the data distribution for this data modeling.
Let me just draw that model, that paper out. How they actually come up with the data collection strategies. It's because I believe that their data collection. Where do they drop that from? Because I don't want to mislead anyone here. So this paper is I think the most recent paper written by a bunch of MIT researchers here. So they are. I have to dig into that to have their whole strategy for data collection. Yeah, but this is the method that they use to do that.
We can't see your screen. That I don't know if you're showing the paper.
You can see the screen. Oh, okay. So the paper is called "Quantifying the Effects of Quarantine Control in COVID-19 Infectious Spread." So let's see their whole. Let's take a look at how the data collection strategies for them. So I believe they combine a few data sources. So let's take a look. So they're using the public available data.
I guess that the question is in relation to their assumption of distribution, whether or not they made the assumption that the data has a specific distribution.
So if they're using a specific probability distribution to model the data, right? I don't see that they mention any particular distribution here from what I see, but maybe I could miss somewhere. Yeah.
Do you have?
No.
Do you have an idea of the modeling technique they use?
So they use differential equations So they use the neural network augmented SIR ODE system to model it. You know, like how they in mathematical biology, so they always use partial differential equations to model population growth. So I think it's similar to, like, maybe there are some relationship between that. But then they definitely use differential like equations to model that growth.
Okay,
Yeah.
and this is just for out of curiosity. The modeling was done based on which, like the which type of data? Is it the number of deaths? Is it number of because you don't have your slides on? And I forgot what it was based on.
Yeah. You mean so so the core okay, let me take a look. I didn't really read through this paper. So let's take a look on that. It's the infection spread within a certain quarantine time to measure the impact of quarantine strength on the data on the infected cases. So it will be like the number of infected people that they're modeling. So I guess that's more similar to that the biological population health population growth model. So that's why they draw in the partial differential equations to model the growth. Yeah, and then so they did one model which is without quarantine control, and then they use the classic for them. It's classic, and it's completely new word, novel word for me. So it's called SEIR, epidemiological model, to model the situation when there's no quarantine control, and then it's a ODE to it's a nonlinear for coupled nonlinear ordinary differential equations to model the subpopulation evolution. So I think, yeah, that they're using the mathematical biology method, so they to model for, say, the evolutional biology model, and then the second model that they use. So therefore, for the ODE model, they have an initial condition. So the initial condition is that there's a starting point 0. So there are 500 infected cases were detected, and then they construct the ODE model, and then an equation, and then they do the parameter estimation for the ODE. And so that's the without quarantine control. And then the second model is with quarantine control. So then they're using a different ODE model. This one is called SIR, epidemiological model. And then so then this one, it's also another ODE with the time t0. The quarantine population at initial point is small compared to the without control, and then construct the initial condition, and then the parameter estimation, and so on. Yeah. That's from what I see this model is.
Okay, that's great. Thank you so much for answering the questions. We have no more questions online. So with that, I thank you and thank the audience for joining us today for your wonderful presentation. Thanks everybody.
Yeah.